Okay, so remember in our first video lecture, enzymes increase rates of reaction. Okay, they're catalysts. Okay, so one way to think about this is that what an enzyme can do is lower the activation energy. For instance, we look back at our conversion of S to P, which is thermodynamically favorable, but perhaps slow, depending on what this activation energy is. Now what the enzyme can do is lower the activation barrier so that this is faster. But typically how it does this is not by affecting the energy of the transition state directly, but instead it finds a different pathway. Okay, so there may be, for instance, two transition states on the pathway catalyzed by the enzyme versus for the native reaction, which is uncatalyzed, there's only one transition state. So if we think about the enzyme catalyzed reaction as having a reaction coordinate shown by this dashed red trace, okay, it's showing a different pathway from converting S to P, but that pathway has a lower activation energy, which allows for the reaction to go quicker. Okay, so let's take a closer look at this. So again, here's our potential well for reactant S and our potential well for reactant P. Okay, so notice again, we now have two transition states. All right, so we have a transition state after the potential well for S, and then we have a second transition state in this after this second potential well, which we call an intermediate. Okay, so the intermediate is a potential well that lies between the reactant and the product here. Okay, so this is the intermediate, and now we have a transition state. Two of these transition states, one after the reactant S and one after the intermediate I, where I is converted to P. All right. And so we can think of this as a two-step reaction. So instead of just thinking of as the overall equation as being S to P, we can think of the reactant S is first converted to intermediate I, and then the intermediate I is then converted to P. But if we cancel everything out, right, the overall equation is still S to P. So the catalytic reaction doesn't change the reaction. It just changes, again, the activation barrier, and it can do that, or the activation energy, and it can do that by finding another pathway for converting S to P. One way to think about this is trying to cross a mountain, for instance. So you can either go over the mountain, right, or you can find another pathway around the mountain that's easier to take, and that's pretty much what enzymes do. Okay, so let's consider this. So let's say we have reaction 1, which is uncatalyzed. So if you want to pause the video and try this on your own. So if this is the uncatalyzed reaction where we have two potential wells, one starting at 0 kilojoules per mole free energy, and the second one, which is product P, which is at negative 30 kilojoules per mole, and then this has an activation, and then the transition state is at plus 15 kilojoules per mole. Okay, what might the reaction coordinate look like for a catalyzed reaction? Okay, so if you want to try that, go ahead and pause the video and draw that out. Okay, so if we look at, for instance, the catalyzed reaction, we might expect a different pathway. Okay, so one thing that needs to be the same is the energies of the reactant and the product wells, right? So remember, a enzyme cannot change the thermodynamics of the reaction. Okay, if the enzyme catalyzes conversion of S to P, right, the change in free energy has to be the same. And so the delta G for the uncatalyzed reaction is 0 plus minus or minus 30 kilojoules per mole. So this would be an overall free energy change of negative 30 kilojoules per mole. So that means the free energy change for the catalyzed reaction also has to be negative 30 kilojoules per mole. Okay, and so since these both have the same free energy, that is totally fine here. Okay. Now, all that should change then. So the answer to this question above is that yes, this can be a catalyzed pathway. Okay. Because the free energy change is identical for both the uncatalyzed reaction coordinate and the catalyzed reaction coordinate here. Okay, and then so what should only change are the activation energy. So the major activation energy for the uncatalyzed reaction is at 15 kilojoules per mole above the reactant potential well. Okay, so that activation energy is 15 minus 0, which is just 15 kilojoules per mole. Okay, versus the highest activation energy here is 8 kilojoules per mole, or rather the energy, the highest energy of either of the two transition states is at 8 kilojoules per mole. Okay, and so this is going to dictate the rate of the reaction here, and this is called the rate determining step. And so the rate determining step for this catalyzed reactant is 8 kilojoules per mole, which is a smaller activation energy than the uncatalyzed reaction, and therefore you would expect the catalyzed reaction to go faster than the uncatalyzed reaction. All right, so that just summarizes what we just said. Okay, so the free energy change is negative 30 kilojoules per mole for both. All right, so that's the thermodynamics have to stay the same, but the second pathway has a smaller activation energy, so it will be faster.